Hello everyone, my name is Noémie Perivier and I am a PhD candidate in the Industrial Engineering and Operations Research Department at Columbia University. In this video, I will present our Sigmetrics 2021 paper entitled Real-Time Approximate Routing for Smart Transit Systems. This is a joint work with Sid Banerjee, Chamsi Hussain, and Samita Samaranayake from Cornell University. The starting point of our work is the observation of the recent transformation of urban mobility due to the introduction of new mobility and demand platforms, such as Uber or Lyft, which have considerably improved the access to mobility for those who cannot afford to own a personal vehicle. Now, the main question is how can we utilize these new advances in mobility in a more scalable, sustainable, and equitable manner? So passengers who cannot afford to have a personal vehicle have now two possible options for transportation, or to use the mobility on-demand platforms, or to use the public transit system. So both these options have advantages and drawbacks. So on the ride-hailing side, it is praised because of its convenience, adaptability, flexibility, but it incurs a lot of negative externalities, such as its huge environmental impact with the congestion, the emissions, and it's still not affordable for most of the population. Whereas the mass transit system is affordable and more environmentally sustainable, but it suffers from a lack of coverage, especially for the low densely populated areas. So seeing this, we can see that these two means of transportation are kind of complementary and would really benefit to be collaborating. However, in the literature, most of the effort have been devoted to improve each of these two solutions independently. So for the ride-hailing side, the effort has been put in developing ride-sharing solutions, whereas for mass transit system, considering a fixed bus network, a trend of literature has tried to develop first and last mile shuttles option. In this paper, we consider a third direction, which is to directly design a multimodal system where we would use the adaptability of the ride-hailing platforms and combine them with the existing public transit system. The goal is to directly design the bus network so as to make it efficient in such an integrated system. Our goal is to design algorithms which are scalable and practical. So we will have to trade off a bit of optimality for practicality. However, we still want to provide theoretical guarantees about the quality of the solutions we output. So our global setting is as follows. We have a platform which has two types of vehicles, the low capacity vehicles, which we call car, and the high capacity vehicles, the buses. And the overall objective is to design a bus line plan and an assignment of passenger to bus and cars, which would maximize utility. We want to consider a real-time problem where we could adaptively design this network in response to the demand. So a closely related problem is the traditional line planning problem, where the goal is to design bus lines so as to cover the maximum trip request, where the demand is given in the form of an origin-destination matrix, so OD matrix, and the goal is to maximize the ridership. For such a line plan, you have some standard constraints, which are the budget and the cost of opening lines, and the fact that you can cover passenger only if enough buses are covering the path they follow. So in this classical line planning problem, you have a trade-off between the ridership and the coverage, because it's highly inefficient to cover all possible origin-destination pairs. And so a lot of passengers have to suffer from that because you would consider only the lines which maximize the ridership. So that's how the current bus networks are designed. So in our setting, we relax a bit the constraint that all the buses have to cover the passenger from their origin to destination, meaning that now the passenger are able to use the mobility on demand platform to join the bus line, then travel on the bus line, and then reach their destination by using again this demand responding service. So we relax a bit the assumption that you have to cover passenger, which allow us more flexibility in the design of the line plan. So now we still want to choose the set of lines that maximize ridership, and we're also interested in designing more to study more precisely the way we assign passengers to line. And in top of the traditional, the standard budget and a coverage constraint, we have an extra constraint, which is that we do not allow inter-bus transfers, meaning that the passenger can only use one single bus during his whole trip. This constraint is theoretically grounded. We show that in our setting, without this constraint, you cannot hope to design an approximation algorithm with a meaningful approximation factor. But it's also coherent on a practical point of view, knowing that the passenger will already use a car to join the bus network and a car to join its destination. So this extra constraint on not allowing bus transfers is also a practical one. So now we'll dive a bit more into the modeling part. So we consider a graph where the cost of the edges are the time travel on the edges, and the platform operates a fleet of buses which have capacity C, meaning that at most C people can use a bus simultaneously. And what we call a line is both a route, which is the path on the network, and a frequency. And for this combination of route and frequency that we call a line, we are given a cost CL. Now the passenger demand is given by a set of origin-destination pairs. And the platform has multiple ways to accommodate this request, or by serving them directly by car. So the passenger will travel from his origin destination by car, or by offering the passenger to do a hybrid trip where he will use one of the bus line and do the rest of the trip by car. So here he would travel on the first 3 edges by bus, and then use a car to join his destination from this node. We can see immediately that there are multiple options for a passenger to use the same line. For instance, he could have traveled by car and joined the middle node, then travel by bus before reaching his destination by car. So the question is, how do we differentiate between all these possible options? And first, we will define what a value for each passenger using a trip option, omega. And this value can be considered as fairly general. And for instance, in order to maximize the system utility, we could say that this value is the reduction in cars, in miles driven by car, as compared to a direct trip by car. So now we define the value of assigning a passenger to a bus line, which is the value that he would get if he, by using the best possible option, which is the one that gives the greatest value. So we can see here that the option omega 2 on the right allows to reduce more the number of miles driven by car. So it has a higher value than the option on the left. And in this case, the passenger line value would correspond to the trip option omega 2. So we can formulate our problem as and give an integer programming formulation for our problem, where the objective is as follows. You have XLP, which are the variables which tell you if you assign the passenger P to line L. And the objective is to maximize the total value of this assignment of passenger to line under the usual constraints. So the budget constraint, the fact that on any edge of the network, you can have more passenger traveling than the number of buses which are covering this edge. And finally, the last constraint, which is that each passenger can be assigned only to a single line, so you have no interbus transfer. So this is a really hard problem because you have exponentially many lines. And one solution to handle that in the line planning literature is to impose the access, to assume that you have an access to a candidate set of lines, which can be large but not exponential. So after using this candidate set of line in the literature, what is done is to iteratively add lines via branch and price. But this doesn't provide algorithm with theoretical guarantee, or it's not computationally efficient. In our work, we propose a new algorithm with which is polynomial time and has good approximation guarantee. So I will present now our approach to solve this problem. So, and first explain the challenges. So if you consider the natural formulation that I just gave, it is closely related to the capacitated facility location problem. And a natural way to obtain a solution would be to first consider the relaxation of the problem and then to try to round it to find a good integer solution. So for the capacitated facility location problem, this can be done efficiently as long as your objective function is submodular. And we can show that for our problem, this is no more the case. So we can't use the standard techniques to find a good integer solution from the fractional solution. What is hard in our case is the second constraint, because when you start from a fractional solution, it's not clear how you would round it to an integer solution while preserving feasibility. Feasibility being that at each, no more than C passenger can use an edge E of the network. So we circumvent this difficulty by introducing a configuration LP, which has exponentially many variables. And now we consider the variables XLS, where S is no more a single passenger, but a set of passengers. And this formulation automatically accommodates the feasibility constraint, because now I consider only the set of passengers S, which are feasible for the line L. So once again, I have a budget constraint and the constraint that all passengers can only be assigned to a line, a single line. So our main technical contribution is to show that even though this LP is exponentially sized, we can still solve it in polynomial time by using the ellipsoid method, for which we can design a polynomial time separation oracle. Then we can show that starting from the fractional solution of the configuration LP, we can obtain a good integer solution by using randomized rounding from using techniques from Fleischer, Gomans, Mirokny, and Sviridenko. So a brief overview, I give here a brief overview of the algorithm. We start with the exponential size formulation. We consider the relaxation of the problem. We solve it using the ellipsoid method. And we interpret the variables XLS as the probability of assigning a set of passengers to a line. Then we do a randomized rounding for each line independently by flipping a coin that tells you the probability to assign this set of passengers to the line. So doing this randomized rounding step may violate the budget constraint. So to handle that, we consider a shrinked budget constraint. And then we do multiple randomized, roundings, and we keep only the best one among all the rounding solutions that were budget respecting. So now we can prove some theoretical guarantees about our algorithm. First, that this procedure will be budget respecting with high probability, and then that the solution, the integer solution output by the algorithm, is at least 1 minus 1 over E minus epsilon, the optimal solution for the original problem. So to illustrate the performance of our algorithm, we've run some experiments. First on synthetic networks. So the synthetic network have been generated by considering an abstract. So you don't really need to know the underlying geometry of the network, as long as you know the candidate set of line, the set of passenger, and the passenger line value for each pair of passenger and line. So we generated a random abstract instances of the problem this way. And we compared the performance of our algorithm with an ILP solver run on the natural integer formulation of the problem. So we give to our algorithm and the ILP solver a strict budget of 20 minutes, because remember that our objective is to be able to recompute the optimal line plan multiple time a day in order to respond adaptively to the demand. And we could show that the ILP solver outperforms us when for small scale instances. But as the instance grows larger, our algorithm had better performances. At some point, the ILP solver was not able to return a solution, where our algorithm was able to return a solution, which is still with good performance. So as the set of line increases, our algorithm outperformed the ILP solver, and similar results were obtained when we increase the size of the set of passengers. So to conclude, I present here some experiment results that we had on the Manhattan network. So we took all the trip requests for mobility on demand vehicles like Lyft and Uber for 1 hour, which is around 10,000 requests. We still run the algorithm under a 20 minutes time budget. And we run it for different values of the budget B of the line plan. And we can see for some values of the budget, our algorithm is able to return a solution, whereas the ILP is no more able to do that. So both for synthetical experiments and experiments on the Manhattan network, we were able to show that our algorithm scales better than the ILP solver. Thank you for your attention, and feel free to ask any question.